Good morning, y'all. Today we're going to be talking about indefinite integrals. Indefinite integrals are the beginning of actually integrating full functions. So we start by this idea of what we call an antiderivative. So if a derivative is to take the derivative, an antiderivative is to work backwards from a derivative. So if I'm given a derivative, f of x, you work backwards to find the original function, capital F of x. Remember back when we did calculus house, I'm like, oh, capital F, that's the integral. We'll talk about it later. So we're talking about it today. So the antiderivative of f of x is equal to 2x is the family of functions, capital F of x is equal to x squared plus c, where c is any constant. Okay, so let's talk about some things real quick. The family of functions, x squared plus c. So what that means is that the antiderivative of 2x is x squared, okay? But I add that plus c because I know when I take derivatives that if I derive like a constant like 4 or 7 or -2, that constant becomes 0. So that c is to account for that constant that might have gone away in the differentiation process. So we add it back for integrals from like, it could be there. Now that constant could also be 0, so there could have never been a constant there, but there could have been a constant there, so we add it back just in case. And the reason why we say the family is because depending on what that constant is, that function could change drastically. It could shift up and down across my graph, depending on what that constant actually is. And so the indefinite integral of a function is exactly that, the family of antiderivatives of the function. So the indefinite integral is the same as antidifferentiation. They're just interchangeable. So let's talk about this notation a little bit more with integrals. So we have this little swirly s, that is our integral symbol. We have f of x, which is the function, but it's also what we call the integrand. It is what we are integrating. Okay, we have dx, which is our variable of integration. So it's going to seem kind of redundant because you're going to be like, oh, we're always going to integrate by x, but we're not. Remember, with implicit differentiation, we can derive x's and y's and t's and all sorts of different variables. So eventually we are going to integrate by things that aren't x. So it is important to understand that this variable of integration tells us what we're integrating by, what variable we're integrating. And then last but not least, this c is that constant of integration, that plus c. Okay, so the process of finding an antiderivative is called antidifferentiation. I know, crazy. Derivative, differentiation, antiderivative, antidifferentiation. Antiderivative and indefinite integral are synonyms. They mean the same thing. So if I ask you to take the antiderivative, or if I ask you to find the indefinite integral, both are going to be the same. And derivatives and antiderivatives are inverse operations. So if I were to derive the integral, that would just equal the function that I have. So just like multiplication and division, addition and subtraction, square roots and squares, all those different things undo each other. Derivatives and integrals are those inverse operations. They do undo each other. So down here in the corner, we got a couple of some basic formulas. So obviously you have all of your trig functions. They're the same ones you know, but backwards. So integration is just all of your derivative formulas, but backwards now, which is crazy. Okay, so your u prime over u becomes natural log of u. Your e to the u becomes e to the u. That one's easy because e is just itself derived, so it's still itself integrated. And then you have all of your trig ones. Sine integrated becomes negative cosine. Cosine integrated becomes positive sine. I know it's weird. You just think of that circle of trig, but backwards. And then, of course, secant squared equals tangent. Cosecant squared equals negative cotangent. Secant times tangent equals secant. And cosecant cotangent equals negative cosecant. So it's all of those rules just backwards. And then, of course, you have up here at the top, it's a really crazy, but it's your power rule. So the weird thing with our backwards power rule is, of course, we do add 1 to the power, and then we divide by that new power. So instead of subtracting and multiplying, we add and divide when we integrate. It's the opposite, that inverse relationship. So let's look at some examples. So number 1, I have the integral of 3 dx. So I'm integrating by x, and you have to think backwards. So what function's derivative is 3? Well, that would be 3x. So the integral of 3 would be equal to 3x plus c. You always have to add that c when you're doing indefinite integrals. It is key and hugely important, okay? And your check, if you want to check, you can always go back and you can derive it. So the derivative, not rectangles, the derivative, so d dx of 3x plus c would be equal to 3x would become 3, and c is just a constant. Remember, it's not a variable, it's the constant of integration. It is a constant, is equal to 0 when I derive it, so my derivative would just be equal to 3. So you can always check your integrals by deriving them back and seeing if you get the same thing. So number 2 over here, we have the integral of just dx. Now, it's not just dx, it is the integral of 1 dx. Remember, in math, we do get lazy. So what would the integral of 1 be? Well, that would be x, because x's derivative is 1. So this would be equal to x plus c. And we're done. All right, the integral of the square root of x dx. So just like we do for derivatives, I can't apply my power rule of integration if it's a square root. So I can change this to be the integral. I really need to figure out my drawing tools. The integral of x to the 1/2 dx. Okay. Now, when I go backwards with my power rule, I add and then I divide by the new power. So I add 1, so this becomes x to the 3/2. I'm adding 1 instead of subtracting 1, and then I divide by the new power. So divide by 3/2, and then plus c. Now, you can technically leave it as x to the 3/2 divided by 3/2 plus c, but that's really, really gross, and you really should not have compound fractions like that. So I can simplify that. Dividing by the fraction is the same as multiplying by the reciprocal. So this becomes 2x to the 3/2 over 3 plus c. And that's my final answer. Okay, let's look at our sign. So the integral of 2 sine dx. So just like we've been doing so far, I can always move constants being multiplied out to the front. So that same constant multiple rule for derivatives is the same constant multiple rule for integrals. So before I start anything, this is 2 times the integral of sine x dx. Now remember, what trig function, if I derived it, would give me positive sine? Well, that would be negative cosine. You can also check over here, my integration rule is that the integral of sine is equal to negative cosine. So this is 2 negative cosine of x plus c. Notice how I don't have 2 times the plus c. Plus c is kind of like this enigma. We just tack it on to the end of the function. We don't, it's not like stuck in the middle of the function. So for my final answer, this would just be negative 2 cosine of x plus c. And of course, y'all, you can always check these by deriving them and confirming that this is the integral by deriving it and getting the same function we started with. So if you derive this and you get 2 sine of x, then you're good. Okay, 5, 1 over x cubed. Once again, another one of those power rule ones where we have to do something beforehand. We have to move it up to the top before we can integrate it, because I can't apply the power rule to a power that's in the bottom of the fraction. So this becomes the integral of x to the negative 3rd dx. Now I can integrate. So add 1, divide by the new power. So negative 3 plus 1 is negative 2. So x to the negative 2 over negative 2 plus c. And as always, y'all, I don't want to leave negative exponents, so I can simplify that to be negative 1 over 2x squared plus c. Just like so. Now, of course, you can leave it in the step before. You won't be counted wrong if it's a free response question, but if it's multiple choice, you'll see that final answer. All right, and then 6, the integral of x plus 2 dx. So I could just integrate this, but just to keep with, it's our basic integrals, same as our basic derivatives. I want you to see all these rules in action. So addition sign in the middle, I can split it up into 2 separate integrals. So this is the same as the integral of x dx plus the integral of 2 dx. Okay. So the integral of x, that is a power rule because what power is on x? That would be a power of 1. So the integral of x is equal to x to the second over 2 plus the integral of 2 to x, and then plus c. So I ignore the addition. I leave it exactly the same. Obviously, if my derivative changes the sign, then that would change the sign. But I ignore it, and I integrate x, I integrate 2, and then I tack on that plus c. So notice, even though I have 2 integrals, I didn't get 2 plus c's, because that's confusing as heck. So we just tack it on as one big plus c at the end. Like I said, plus c is just kind of that, we tack it on to the end of our integral. Like, oh, you're done integrating? Okay, plus c. It's not an extra variable or something that we have to work with. And there you go. Couple more. Getting just a little harder. So now we have the integral of 3x to the fourth minus 5x squared plus x dx. So this time I'm not going to break it up. We're just going to go straight forward. So these are all power rules, constant multiplied, sum and difference. So we're going to ignore the constants being multiplied in the front. We're going to leave the signs the same, and I'm just going to deal with my reverse power rule. So this is equal to 3 power plus 1 x to the fifth over 5 minus 5 power plus 1 x to the third over 3 plus x power plus 1 squared over 2 plus c. And I went a little over on my room, but that's okay. So notice everything. Subtraction, addition stayed the same. Constants being multiplied, 3, 5, and 1 stayed the same. All I did is I looked at the x's. So x to the fourth became x to the fifth over 5. X squared became x cubed over 3. And x became x squared over 2. So notice while with our power rule with derivatives, we get those numbers being multiplied in front. With integrals, we get those numbers being divided on the bottom. So opposite inverse relationships create opposite inverse functions. So 8, the integral of x plus 1 over square root of x. All right, well, this looks like a quotient rule. And you're like, Mr. Arbone, we're throwing quotient rule out on the first day too? No. Okay, so before we can do this, y'all, just like we would for derivatives, we can simplify this a bit. So x plus 1 over the square root of x is the same thing as the integral of x to the first over x to the 1/2 plus 1 over x to the 1/2. So I can not only change that square root into a power, but I can then split up that fraction. And then this is still dx. Okay, so now I can reduce these more. If I have same base with the powers, I can subtract the powers. So 1 minus 1/2 is equal to 1/2. So this becomes x to the 1/2. And then that x to the 1/2 in the bottom becomes x to the negative 1/2. And then still dx. Now, just like before, I'm going to add 1 to both of these powers. So this becomes, the integral is 1/2 plus 1, which is 3/2, divided by 3/2, plus negative 1/2 plus 1 is positive 1/2, divided by 1/2, and then plus c. And because those are gross, I always want to get rid of those compound fractions. So multiply by the reciprocal. So this becomes 2x to the 3/2 over 3 plus 2x to the 1/2 plus c. And we're done like so. All right, last two down at the bottom. So these are ones where you're like, well, I can't do quotient rules still, so we're probably going to have to simplify using some trig identities. 1 plus tangent squared, I can integrate 1, but I don't know an integral for tangent squared yet, so I'm probably going to have to use a trig identity there. So remember, sometimes with these basic integrals, just like with our basic derivatives, we're going to have to simplify first. So sine over cosine squared, well, remember that I can split this up into sine of x over cosine of x times 1 over cosine of x, and that's still dx. And that becomes sine over cosine is equal to tangent. So the integral of tangent of x times 1 over cosine is equal to secant of x, and that's still dx. Now, tangent x, secant x doesn't look quite like our rule. I think our rule is secant times tangent, but tangent times secant, secant times tangent, those are the same thing. So the integral of that is just secant. So this is equal to secant of x plus c. Nice and simple. So the hard work was the simplifying. The integral was easy in the end, right? Last but not least, we have 1 plus tangent squared. Well, if we know our Pythagorean identities, 1 plus tangent squared is equal to secant squared. So this becomes the integral of secant squared of x dx. And then once again, from our rules, I know the derivative of tangent is secant squared, which means the integral of secant squared is equal to tangent. So this becomes tangent of x plus c. So integrals, they're just derivatives backwards. Pretty crazy, right? Okay, last but not least, we're going to actually solve for those values of c. So right now, what we have is a differential equation. Okay, an equation that involves x, y, and y prime. So like a derivative. So anytime you have a derivative, that is a differential equation because it involves x, y, and dy over dx. Okay, it's kind of like an implicit derivative that you've already taken the derivative of. You got the derivative, you got y, and you got x. Okay, what we found over here with our integrals are also what we call the general solution. Okay, the general solution is kind of think of it as like, remember when I said the family? It's the solution that could go in a lot of different ways depending on where I decide my function actually lands. So it's general. It's depending on the situation, my function could be a lot of different things because I still don't know what that c is. That c is still an unknown constant. Okay, c is the constant of integration. It's unknown, but we tack it on there because we know there could be something. So that's why it's general. It's still kind of unknown. It's in general. A particular solution is obtained by solving for c in a general solution with a given initial condition. So if I give you a value to plug in for x and for y, then you can actually solve for what that c value is. So let's look at an example. I have f prime of x is equal to 3x squared minus 1, and I'm told that f of 2 is equal to 4, which just means my x value is 2, my y value is 4. So we're going to go ahead and integrate. And when integrating a differential equation, y'all, the thing you should notice is it's an equation versus something like this, where it's kind of just like an expression. Okay. So I have two sides to the equation, so I'm going to integrate both sides. Okay. The integral of f prime of x is just f of x. And the integral of 3x squared minus 1, I'm going to do my integration rules. So that becomes 3x cubed over 3 minus x, and then plus c. And I can simplify that just a step further to make it f of x is equal to x cubed minus x plus c. Okay, so that's my integral. My derivative was 3x squared minus 1. My integral is f of x equals x cubed minus x plus c. Okay, and that matches up. Derivative of x cubed would be 3x squared. Derivative of negative x would be negative 1. Okay, now I can plug in to get my value of c. So I'm going to plug in 2 for x and 4 for f of x. So 4 is equal to 2 cubed minus 2 plus c. So I'm just going to solve for c. So 2 cubed is 8 minus 2 is 6. So 4 is equal to 6 plus c, minus 6 to both sides, and we get negative 2 is equal to c. And then I can just plug that back in to get my exact function. Like so. Okay? So this right here, our original derivative, or our original integral, sorry, is what we call the general solution. Not squares. So this is what we call the general solution. Right here is what we call our particular solution. Okay. So I'm going to let y'all practice it real quick with number 11 and number 12, and then you can check your work here at the end. All right, also, just so we can check our work on both, so the integral of 1 over x squared, I can change that first to x to the negative 2. When I integrate that, that becomes x to the negative first over negative 1. Add 1, divide by the new power. I plug in 0 for y and 1 for x. That gives me c is equal to 1. And then I just plug that back in. F of x is equal to negative 1 over x plus 1. All right, for my second one, they start us all the way at the second derivative and give us an initial condition for the first derivative and for the original function. So we're just going to repeat the process twice. So if you got a little stumped by that one, that's okay. You can check your work now, and hopefully it makes a little more sense. So we integrate the second derivative first. So integral of f double prime is f prime. Integral of x squared becomes x cubed over 3 plus c. Plug in our initial condition. We get c is equal to 6. So then we plug 6 in, which gives us f prime of x is equal to x cubed over 3 plus 6. Integrate both sides again. So we're repeating the process. So f prime of x becomes f of x. X to the third over 3 becomes x to the fourth over 12. So I add 1 to that power, and then dividing by that new power, it's just like we multiply the numbers in the bottom of the fraction. So 3 times 4 is equal to 12. So x to the fourth over 12 plus 6x plus c. Plug in our initial condition again, get a new c value of 3. We plug in for that new c value, and we get our final function of f of x is equal to x to the fourth over 12 plus 6x plus 3. So that's anti-differentiation, y'all, and indefinite integrals. We're going to get more practice with this in the coming weeks, so have some fun with it here right before break, and when we come back, we're going to really hit integrals hard. But thank y'all.